This video demonstrates how to analyze data in R using one-way ANOVA and contrast analysis. So first we just need to set up our session. Notice we have several packages we're going to load to do different things, and then we're going to read in the data. And so this is a new data set, calling it expectation. And so what they did here was they used participants sort of as experimenters, and they told them that either that they were going to be showing other people pictures, and that the people in the pictures were either high or low in their appearance of success, even though all of the pictures were the same, and also of people who were pretty average in appearance. That was one manipulation. And then the other manipulation was this instruction variable, where they were told to get good data, scientific data, or in a control condition they weren't told anything. And then this is the rating from the actual participants that these experimenter participants were guiding through the study. Okay, so the first thing we want to do is to get some basic descriptive statistics. So we're using the tapply function. And all of the apply functions are pretty helpful. T just means it's going to return it in a table, so it'll be pretty easy to read the output. The first variable is the outcome variable we're interested in, so in this case the rating that was given by the real participants. And then the instruction, one of the manipulations that was used, and then we're going to use this stat describe function that comes from the paste CS package. And this will give us a lot of output, and since we're using tapply, it gives us that output for each level of instruction, so good, none, and scientific. And then we have the number of valid cases in the data, the minimum value, the maximum value, the range, the sum, the median, the mean, the standard error of the mean. This right here will allow you to create a 95% confidence interval around the mean. So this is the value that you would subtract and add to the mean itself, the variance, standard deviation, and then this coefficient of variance is the standard deviation divided by the mean. So you get lots of information, more than you would even need to report, but it's a good way to really see what's going on with your data. If you want more specific output, here we can use the same tapply function, but now we want to get means for each group. So here we have the means for each group. We can do the same thing with standard deviation, and then we're using the table function with the instruction variable, and that just tells us the sample size for each of our groups. And now we can test for homogeneity of variance. So first we're going to use tapply again to get the variance of each group, and then we can use the Bartlett test to test whether these variances are different across the groups. So our outcome variable is rating, and our grouping variable is still instruction. We're telling it what the name of the data set is. And so here we see that there is a significant difference. So we actually do have difference in our variance across our groups. If we do this again, we can see we have a lot of variance in the good condition. So when the participant experimenters were told to get good data, there was a lot more variance there, followed by if they weren't told anything. And then the least variance was when they were told to get scientific data. So this means we need to correct for actually not meeting this homogeneity of variance assumption. Okay, so next we're going to look at just the ANOVA itself, checking some other assumptions and doing some post hoc tests. So we'll start with the equal variances just because it's more typical of what we do. So even though with this data we would be doing the unequal variances, we're going to look at this one first. So ANOVA.1 is just the name of the model or object that we are creating. You can call this whatever you want. But into that we're putting AOV, so this is one of the functions that you can use for ANOVA, where the variable rating sort of is being predicted from instruction. That's our grouping variable. Again, we're telling it the name of our data set. So when you run that first line, you don't get anything. You have to ask for summary ANOVA.1, and then once in what is in the parentheses has to match the object you just created. So now we have some output. So we have the instruction row, that's our between groups variability. Residuals, that's the within groups variability. Notice we have degrees of freedom first, which is not what we've been doing when we did it by hand, but that's what comes up first. Then you have your sum of squares, the mean square, the F value, and the P value. So this is telling us that our group means don't differ. Okay, and then since we did have a significant Bartlett test, we actually should be using this Welch correction that deals with having unequal variances. So let's see how much that changes our output. So if we run both of these together, the summary and the one-way, then we can compare that output more easily. So F value went from 0.8 to 0.99, P value from 0.44 to 0.37, degrees of freedom between from 94 down to 60. So there are definitely some differences, but our conclusion is still the same, that the groups don't differ. Okay, to further check the assumptions, we can run this plot function, but it's kind of weird that in order to check the assumptions, you actually have to run the model first. We have to create this ANOVA.1 in order to do the plots, which is the same as what we had to do in regression. So it should look familiar. So we have 4 different plots it creates. So this is the residuals versus fitted plot, and this is another way to check for a homogeneity of variance, and there should not be a pattern or a consistent change in the residuals across the x-axis. So these dots across the x-axis should look all about the same, but notice that we have quite a bit more variability here on this end than we do on others. So that's another clue that our variances are not equal. The normal QQ plot tells us whether we have outliers. So all of these dots, to not have outliers, should be right on the line, but as you can see, we have several. So observation number 7 is not very close to the line. We have several down here. We have 77 that's identified for us. We've got a couple of outliers, at least one on each end, if not more on the lower end here. And then we have the scale location plot, and this is similar to the residuals versus fitted, that again we would want the same amount of variability, and you can see we have some differences and it also drops a little. And then finally the residuals versus leverage plot, and this tries to identify points that might have more influence than others on the outcome and therefore might be outliers. So anything that is identified, you should look more carefully at that data point. So 7, 1, and 77. And now we're going to look at post hoc comparisons. First, we're going to use the Bonferroni, and so we're using the function pairwise.t.test. Still, rating is our outcome variable, instruction is our grouping variable. Paired equals false. We need this to tell R that the kind of t-test we're using is not a paired test, so it's an independent samples test. And then we're adjusting the p-value using the Bonferroni method. And so here's our output. And what it does is it compares each pair of groups. So none versus good, and these are the p-values, is 1. Scientific versus good, 0.66. Scientific versus none, also 1. So obviously these are all much larger than 0.05. So there are no differences between the groups. And if you want to do a pairwise test without using the Bonferroni adjustment, you can take just the first part of this line. Right, so this would be unadjusted. Need to close our parentheses so it will run. And then if we run that, we get the output looks the same. This time the adjustment method, the default Holm method. And so we can still see there's no differences among the groups. Okay, and then next we're going to look at the Tukey post hoc test using this GLHT function, which is the general linear hypothesis, is what that stands for. We tell it the name of the object we created, so we're just using this ANOVA.1. Don't worry about what this means. Really the important piece is that we're telling it that we want a Tukey test. So when we first run this, we don't get any output. We have to ask for the summary, and then right here are the hypotheses that are its testing, basically that there's no differences between each group. Here is our estimate, standard error, t-value, and p-value, right? We can see very quickly and easily that there are no differences between any of the groups. We can also get a confidence interval around the estimates, so this is the lower and the upper confidence interval around this difference. And then we can also get a plot with the confidence intervals, so this is super nice to look at. So this is the hypothesized value of no difference between the groups, and as you can see, all of the groups have both very wide confidence intervals and ones that clearly overlap with 0. All right, so now we can look at effect sizes. So first we're going to do the overall effect size just in terms of eta squared. So we're doing a summary.lm, where LM stands for linear model, not save ANOVA object we've been using the whole time. And so what we want to look at here is the multiple r squared. So that is our eta squared value, about 0.02. And then we can also calculate effect sizes for pairs of our groups. So MES is the function. And then what these numbers are, the first two numbers are the two means that are being compared. And then we have the two standard deviations that are being compared, and then the two sample sizes for each of these groups. So this is not a super user-friendly function because you have to calculate the means and the standard deviations and the sample sizes, which we did earlier when we described just the basic descriptive statistics of the groups, but you have to do that and then type the numbers in here. But once you do that, you get lots of good output. So you get effect sizes in terms of D, Q, also correlational effect sizes in terms of R and Z, and then an odds ratio and a log odds ratio. I think this D is certainly one of the more useful ones to consider. So an effect size of -0.31 with a 95% confidence interval around that. The p-value is not significant. And then also we get the R effect size with also the 95% confidence interval and then the associated p-value. Next, we can look at power. And so this function, pwr.anova.test, takes several different types of information. So K is the number of groups, N is the number of observations per group, F, this is the effect size, and it's similar to Cohen's D, the significance level you want to set, and the power level. And so you add information for all but one. So in this case, we left N equals null, and then that's what will be returned is the sample size that will make all of these other parameters fit. So a balanced one-way analysis of variance means that all of our groups are going to have the same sample size. So it's giving us back the information we gave it, but now it's filling in the sample size. So we would need 53 people per group in order to detect an effect of about 1/4 of a standard deviation with a alpha level of 0.05 and a power of 0.80. And so this is where I was saying you can actually easily play around with this power. What if we drop it down to 0.70? So now rather than a sample size of 53, we have a sample size of about 42. So it's kind of nice to be able to see what happens. Or what if we thought our effect was a little bit stronger? What if we thought it was 0.30 instead of 0.25? Right now our sample size is even a little bit smaller because it's easier to detect a bigger effect. So it's a good idea, again, to look at this different ways. What if I change my effect a little bit? What if I change the power that I'm looking for? How much does that change the sample size that it would then be needed to detect that? All right, and then this last piece is for contrast analysis. So the function is fit.contrast. Again, we have to use this ANOVA.1 object we created, so you actually have to run the ANOVA first. Instruction, that's the grouping variable. C, and then in the parentheses, this is the set of contrast weights. So 0, -1, and +1. And the groups are going to be ordered within the data in terms of alphabetical order, which we saw, if you weren't sure what that order was, when we did the t-apply up here, it gives us the order, good, none, and scientific. So that's what has to match when we put in our contrast weights. So good would be 0, this would be the none prediction, and then the scientific. And then we can also get a confidence interval, like 95%. And df equals true just means that you want it to print back what the degrees of freedom are. And so it tells us again what our contrast weights are. Gives you the estimate of the contrast, standard error, t-value, the p-value, the degrees of freedom, the lower confidence interval, and the upper confidence interval. And you can see that this confidence interval is around this estimate, not around the t-value. So that's the estimate you would want to report with this confidence interval. And again, sort of similar to there not being any difference between the groups, we're also seeing that these data are not consistent with the prediction.